conservative force is the force from a spring. And so when we calculated the work that was done by a spring, we found that it only depended on where you start in terms of stretching or compressing the spring and where you end up in terms of stretching and compressing, and doesn't depend on the path that was taken to go from the starting position to the ending position. So we know the work done by the force of a spring, where it's a spring block system, depends on the initial position of the spring relative to equilibrium and the final position of the spring relative to equilibrium. And the work done by the spring is 1/2 the spring constant times that initial position squared minus 1/2 the spring constant times the final position squared. Because the work done by the spring only depends on where you start and where you end up, we define a potential energy associated with this conservative force, and it's called elastic potential energy. And the elastic potential energy for a spring is just 1/2 kx squared. And by writing it in this way, we can say that the work done by a spring is just the initial elastic potential energy minus the final elastic potential energy. But this is energy stored in the spring, in the system. If a spring is stretched or compressed and then is released, that stored energy that it has from being displaced from equilibrium can be converted into kinetic energy. So here is a spring that has a mass on it. Right now it's in its equilibrium position, so that's what that dotted line is. I'm going to go ahead and hit play, and we can see over on the left that the energy, and I'm going to pause it. There we go. So here we have kinetic energy of the mass. Here we have gravitational potential energy because it is raised above some reference position here, which is the 0 position. And it also has this lighter color is elastic potential energy. And we can see that as the mass moves up and down, it's changing the kinetic energy, the amount of gravitational potential energy, and also the elastic potential energy. So now I have a lot of elastic, a little elastic, right? So as it stretches all the way out here, there's a lot of potential energy from the spring. And then when it gets to the highest position, it has a lot of gravitational potential energy. And in the process, those potential energies are being converted into kinetic energy, or energy due to motion. The diagram over on the right is, we're going to end up talking about this, but the total energy of the system, if I were to add together the kinetic energy, the potential energy due to gravity, and the elastic potential energy, we see that they always add up and they're staying the same exact value. It's different amounts of each, but the total amount of energy in this case is staying the same. Now, if I add some damping to this, meaning like some air resistance, we'll notice what happens. I'm going to put like a medium amount. So it's really slowing down because we are losing energy like kinetic energy and gravitational potential energy due to the air resistance, and that is being converted into this thermal energy right here. But this is just an example of how you can have both forms of potential energy, gravitational potential energy and elastic potential energy, and have it be converted into kinetic energy. So now we've talked about conservative forces, and we've got two conservative forces, the force of gravity and the force from a spring, elastic force. So all other forces that we've talked about are non-conservative forces. One example of an obvious non-conservative force is friction. So the amount of friction depends on the path that you choose. So if you were to push a book from A to B, the frictional force would oppose the motion, and there would be a certain amount of work done, and that work is based on the displacement along the blue path here. But if you push the book from A to B along the curved path, there would be a different amount of work done by friction because of the fact that the frictional force always opposes the motion, and there's a bigger path here, a larger distance. So this picture here is just sort of showing what can happen if you have a block that is in motion and it has some initial velocity. If it was going in a straight line, it had some initial velocity, it goes through some displacement, and eventually it comes to rest. So it starts off and it has kinetic energy. There's no internal energy, there's just some total energy of the system, and as it moves, work is done by friction, and so it loses kinetic energy, and that energy that it loses goes into internal energy, which would be thermal energy. But we could talk about the total energy of the system staying the same. Eventually, when it comes to rest, it doesn't have any kinetic energy anymore, and all of that kinetic energy that it had was used by friction, and that was converted into internal energy or thermal energy. So when we think about potential energy, we can think about the total amount of potential energy for a system, or a total amount of stored energy. And so if we have an object that's raised above the ground or above some reference point, it has gravitational potential energy. And if we have a spring and it's stretched, it has elastic potential energy. And so the total potential energy of a system is just the potential energy due to gravity, which depends on mass, gravity, and the vertical position. And it depends, and then you could have elastic potential energy, which depends on the spring constant and how much it's displaced from equilibrium. In general, the net work done by these two non-conservative forces is just equal to the initial potential energy that you start with minus the final potential energy, which is just minus the change in potential energy. But this is now true for all of the conservative forces that we have, both gravitational and elastic.